So a very pleasant good afternoon to all and welcome to 5 days faculty development program on innovative research and development trends in electronics and communication engineering. Organized by Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management, Greater Noida. This program is technically co-sponsored by IEEE UP section, IIC, Startup UP, and AKTU University. Thank you for taking time out and being here today. We are very grateful to have here with us for today's session Dr. Vishal Kesari, and the agenda for today's talk is vacuum electron-based medium to high-power oscillators and amplifiers. Before that, before we start this session and we listen to our distinguished speaker, I would like to give a short PPT about the department so that our speaker and participants are being regularly, they are seeing this video, but yes, we do want to interact with the speaker and want to let you know that who we are as an organization as well as department. So we have prepared a short PPT. So please, it will take just 5 and 10 minutes more. So I'm just sharing my PPT. Is my slides visible?
Yes.
Okay, thank you. So before starting about the department, I would like to introduce our institute, that is GL Bajaj Institute of Technology and Management. It is one of the prestigious institutions under GL Bajaj Group of Institutions. It is one of Uttar Pradesh best engineering and management colleges and is known for providing its students quality education and great placement opportunities. It is approved by AICTE, MHRD, Government of India, and is affiliated to AKTU University. This is about our department. Our department visions to become a department of repute and prepare globally competent and socially responsible professionals with holistic knowledge and technical skills under the mentorship of Dr. Satendra Sharma, HOD, Department of Electronics and Communication Engineering. We are happy that our EC department is NBA accredited and we offer BTech course of 4 years. And this department has been established in 2005 and have always exerted the best of its effort to meet the objective of achieving technical excellence in areas of electronics and communication engineering. These are some of our highlights of department. So since the inception of the institute, the department has also been established in 2005, and the department started with 60 seats, but now we are witnessing the growth in the number of seats. We are offering 180 seats right now. And also our institute is providing #1 ranking in results. Recently in 2021, we have ranked first in Uttar Pradesh, the first semester result. And also the research credentials are available in our department. We have here 5 research groups. Almost 20 plus patents have been filed and published and are also currently we are doing it. Our students are very dexterous and approximately 15 lakhs has been awarded to the students in grants and various other awards. We have here 11 laboratories, 6 advanced laboratories, and dedicated faculties are publishing a good amount of papers as well as quality articles in various reputed journals. And we have been out across like 300 plus research articles.
Ma'am, I think your mobile is also on. Double sound is coming. Just please check. Switch on, switch off.
No, from my end, it's not. I think so. From the speaker end, mic is.
May I request Dr. Vishal Kesari to put your mic in mute mode? Yes, ma'am. Please go ahead.
Okay, thank you. So also we as a department, we are providing 360-degree focus on student development. We are focusing on all the coverage, that is state-of-the-art laboratories, highly qualified faculty. We also annually organize international conference, MedCom. and the papers are published in reputed Journal of Springer. This time, this conference is going to happen in October, and we are receiving huge participation from not only national but internationally as well. So we invite you also. Please, you feel free to send your papers and get registered. And also, we are organizing international webinars, FDPs, STPs, workshops, and we are working on research, innovation, and incubation support to the students. We provide 100% placements and alumni interactions. We have at the department Anvita Club and Tech Blitz to develop their overall personality and focus on the extracurricular activities as well, apart from academics. We also invite renowned people for guest lectures from academics like IITs, NITs, and leading industry experts. We at our department have NPTEL local chapter, ICEIT GL Bajaj student chapter, IEEE GL Bajaj student chapter, as well as department newsletter and journal. These are the some of the best brains to mentor the bright mind. These are the faculty list, and we are proud to have such dedicated faculty members here in the department. And these are the advanced laboratories, 6 advanced laboratories which we have for our students to make industry ready. So we have here as Cisco Networking Academy, we have Technology Incubation and Development Center. We do have Center of Excellences in Biomedical, Image and Signal Processing, as well as SDR and Minor Systems. We have Research and Development Lab, as well as CNC-based PCB routing. These are some glimpses of our student achievements, and we are very proud that one of our students, that is Kajal Srivastav, her project was selected amongst Pan India, and that was also among only 5 projects which were selected to be showcased in front of Prime Minister Shri Narendra Modi and Prime Minister of Israel, Mr. Benjamin Netanyahu. And also, our students are actively participating on various platforms like Anveshna, and they're bagging prizes. On top 3, always they are coming. So this is the highlights that you can see. They are also participating in Startup Awards, and they have received around rupees 10 lakhs as fund from Atal Incubation Center and NXG Venture. They have also bagged prize from Divisional Innovation Exhibition, which was supported and catalyzed by Council of Science and Technology UP, partner of the Department of Science and Technology. Also, the students have participated in and bagged prize in Technovation hackathons and are actively participating in many such competitions and are winning. They are coming up with prizes, so that's what we are always proud of. And also, our students are not only like participating in competition, they are representing as delegates in global platforms like Women Economic Forums, and the department has signed MOU with the ALTTC, BSNL Ghaziabad. This is a highlight about the placements. So we at EC department, this year only, we have witnessed record-breaking placement of 92%, and the highest package has been gone to 18.2 lakhs in Cisco. And these are some of the top recruiters for the current batch, that is EC 2020 batch. So we had with us very reputed collaborations. You can see the recruiters, Cisco, Bosch, Ericsson, Accenture, and many more. And also, our students, they are very creative and innovative, and they are moving ahead in this entrepreneurship journey, and they are establishing their venture successfully. So this is the startup which the student has made, that is CEO of his own startup company. And we at a department are organizing very informative webinars, and we are getting appreciation not only from national front but international front. Recently, for this present year, we have organized many webinars on very interesting topics, and we are going to organize much more than that. So we look forward for more such collaborations. Our students, we take students to industrial visits in reputed organizations like ST Microelectronics, LTTC, Electronica, Uniconverge Technologies, Ministry of Electronics and Information Technology, and many more. These are some of our notable alumni, and they are serving in reputed places like Indian Army, Indian Air Force, ISRO, or Ministry of Defense, Malaysia. They are being present all over the globe, and we are proud to have them as a GLB family. So this is all about our department, and if you want to reach or contact us, please feel free to write at this given email address. So this is all about our department. So now I will request Dr. Jaishankar Kesri sir to introduce our speaker for today.
Thank you, ma'am. Thanks a lot, ma'am. Good afternoon to all, one and all. On behalf of GL Bajaj Institute of Technology and Management and Department of ECE, I, Dr. Jaishankar Kesri, Associate Professor, ECE Department, would like to give a warm welcome to our honorable speaker of the day, Dr. Visal Kesri, who is a senior scientist in DRDO and world-renowned researcher in the domain of microwave tube research and waveguide structure. I feel privileged and proud to read the profile of Dr. Visal Kesri. Dr. Visal Kesri received PhD degree in electronics engineering from Indian Institute of Technology, IIT BHU in the year 2006. He has worked as research fellow at Center of Advanced Study, Electronics Engineering, Department of IIT BHU, and significantly contributed to a sponsored research project at Center of Research in Microwave Tube, IIT BHU. He served as lecturer at Birla Institute of Technology, Ranchi, India, and Indian Institute of Information Technology, Allahabad, India, before joining as scientist at Microwave Tube Research and Development Center, Defense Research and Development Organization, Bangalore, India. His research interests include microwave and millimeter wave vacuum electronic device and modules. He has authored and co-authored 4 books of highest repute. First book is High Power Microwave Tube, Basics and Trends, IOP Concise Physics, Morgan and Claypool, publisher San Rafael, California, 2018 in 2 volumes. His second book is Analysis of Disk-Loaded Circular Waveguide for Wideband Gyro Traveling Wave Tube, that is from Lambert Academic Publishing, AG and Company, Germany, 2009. Third book is Sukshma Tarang and Millimeter तरंग निर्वात इलेक्ट्रॉनिक युक्तियां एवं संबंधित तथ्य, डीआरडीओ विशेष प्रकाशन श्रृंखला, रक्षा अनुसंधान एवं विकास संगठन, रक्षा मंत्रालय, नई दिल्ली, जनवरी 2019. एंड हिज फोर्थ बुक इज निर्वात इलेक्ट्रॉनिकी एवं कार्यालय प्रशासन शब्दावली संकलन, सूक्ष्म तरंग, नलिका अनुसंधान तथा विकास केंद्र, रक्षा अनुसंधान तथा विकास संगठन, रक्षा मंत्रालय, भारत सरकार, बेंगलुरु, 2021. And more than 120 research papers in peer-reviewed journal and conference proceedings. Taken various editorial responsibility for developing the conference and webinar proceeding, MTRDC and DRDO newsletter, etc. He has to his credit a number of international and department level awards, including DRDO Young Scientist Award 2012 and Titanium Medal Award 2019. He has acted as reviewers for various peer-reviewed journals like IEEE, Springer, Teller and Francis, Elsevier, IT, Progress in Electromagnetic Research, etc., and conference proceeding. He has been recognized as Golden Reviewer of IEEE Electronic Device Letter for the year 2014, 2015, 2018, and 2020, and of IEEE Transaction on Electronic Device for the year 2014 to 2020. He is Fellow of Institute of Electronic and Telecommunication Engineering, India, Life Member of Vacuum Electronic Device and Application Society, that is BEDAS, India, and Executive Member and Administrator Thinkers in BED Group, India. Thank you, sir, and a very warm welcome to you, sir. Now, I hand over the mic to our Head of Department, Professor Dr. Satyendra Sharma, sir, to please welcome our speaker, Dr. Visal Kesri. Thank you, sir. Thanks a lot, sir.
Thank you, Dr. Jay. Good afternoon to one and all present here. Respected guest of the day, Dr. Vishal Kesri ji, all participants, HODs, and dear faculty members and staff. Really, after listening the biodata of Dr. Vishal Kesri, I find you are the richest person available in technology. The what topic you have suggested, I have reached mentally to 1985 version where I have worked 6 years involved technology. First, when I was working in radar, one of computer that was known as approach line computer and which was made of vacuum tube and valves. I have worked 5 years in that technology. So naturally, even nowadays, this generation may not be knowing what is triode, what is tetrode, what is pentode, what is hexode. And all together I have seen diode, triode, tetrode, pentode, hexode. It was making one computer that was known as approach line computer of radar of Valve technology. So this technology you are going to present here, really I am very much thankful to you that you are taking such a vacuum tube electrons. It's a very vast technology and I am really eagerly waiting to listen from you. Sir, you are the very respectful person from very respected place. And I know some secrecy, it has to be maintained all the time because you are our heart of this nation. So I welcome you. You have spared a very crucial time from your busy schedule. So on behalf of GL Bajaj management, our EC staffs, I welcome you. Thank you, sir. Thank you very much. Please take over the dais and enrich with some technology so that we can also follow and move ahead. Thank you very much. Mic, sir, mic.
Sir, your mic is muted, sir. So not, yes, no, it's
yes.
I think you are. I'm audible now.
Yes, sir.
Yes.
Yes, audible.
Okay, thank you very much for a nice introduction. So let us go into the business. We will start with our. I will try to share my presentation. Am I visible to all?
So the screen is not sharing right now.
Okay. Ram?
Yes, sir. Now your screen is visible. Yes, sir. And can press on hide button. So no content will be like, yes. Yes, sir. Your PPTs are very much, we are able to see, sir. Sir, we are not able to hear you, sir.
Ram, can you check mic?
Now you are audible, sir. Now you are audible.
Okay, fine. So, should we start now?
Yes, sir.
Okay. So, today what we are going to talk on, that is vacuum electron based medium to high power oscillators and amplifier. Okay. So now if you see the title, we are going to talk about vacuum electron based some devices which may be amplifier and oscillators. And we are going to talk about medium to high power. So what we are going to fix the agenda, what we'll do, we'll be talking something on oscillator and amplifier of one category, which will be towards the medium power level, and the another category which will be at high power level. So today we are going to talk about in general 4 devices. One is there that magnetron, which will be slow wave device, and it is an oscillator. The second one is traveling wave tube, which is an amplifier and slow wave device. The other side, when we are talking about the high power side, then we are talking towards the oscillator. We are going to talk about one device, it's called gyrotron, and the another device which is gyro traveling wave tube, which will be an amplifier. Okay, so actually, as we know, we are celebrating 75th years of our independence. So this lecture I am dedicating for Azadi Ka Amrit Mahotsav as plan of our Honorable Prime Minister. Fine. So let me start with where I am working. So you can see on the screen, there is a Google map, and in center, a typical heart shape structure you can see, that is nothing but Bangalore. And in one of the side, you can see one circle, which is MTRDC, that is Microwave Research and Development Center. So in that, we have 2 of our building. One is the main block, and the second one is JC Bose Traveling Wave Tube Facility. Not going much in detail, we are again occupying one more building, which is a bigger building somewhere here, which is a 4 floors story. That is, we are going to recently, we have acquired, and then building is now ready to move. So we will be having total 3 buildings in our premises. Coming to the next about MTRDC. So our vision is to anticipate the microwave powered products needed, establish the technique, and to develop the right item at right time. Fine. Then remaining all other details, what we see actually, basically it's always like what is the charter given by Government of India to us to start our work. So that charter is to conduct research and development activity in the field of advanced microwave tube required in the country and aspect related to their application and engineering. Our quality policy, design and development of advanced microwave power devices or modules, meeting user requirement by country by continually improved CAD tools, technology, quality management system, and by adopting risk-based thinking. Our core strength is towards design and development of microwave tubes for EW and radar applications, design and development of electronic power conditioners, microwave power modules and transmitters, then engineering and technology is required for microwave tubes. Okay, now coming to my end, what technically I do. So basically I'm a project director for one of the project, which is design and development of medium power broadband microwave power module. This power module contains miniature helix traveling wave tube and electronic power conditioner. We generally take care for design, development, measurement, characterization, testing and qualification. And whatever related optimization is there for process and technology, that also we take care. Another project which is towards the high power, that my group work on design and development of millimeter wave gyrotron. This is a class of oscillator where we work for design, development, measurement, characterization and testing. Here also, because actually it is going to be a technologically challenging area, so optimization of process and technologies are needed. Additionally, I do theoretical studies on gyro traveling wave tubes, then some simulation studies for innovative subassembly, which is required for various vacuum electronic devices. Okay, at the outset, I would like to acknowledge, I would like to thank Professor Satyendra Sharma, Dr. Astha Sharma and his team from GL Bajaj Institute of Technology and Management, Greater Noida, for inviting me for this talk. Further, I definitely acknowledge my colleagues whose data or results I am going to use in further slides. Further, some of the data is taken from open domain. I further acknowledge that also. A special thanks to Professor Jashankar Kesari of GL Bajaj for establishing link between me and GL Bajaj. Okay, now let's start the technical activity. So here on this particular screen, you can see that electromagnetic spectrum is seen. In the second row, you can see there is a radio waves and it keep continuing up to the gamma ray. So when we are talking about radio, when our wavelength is quite high, and when we are talking about gamma ray, wavelength comes down. So now in this full spectrum, if you see the size of the wavelength, it is something comparing with the building towards the radio wave, and when you are going towards the gamma ray, we are talking about the size of atomic nuclei. Here, if we divide, when we talk about microwave side, then down you can see there is a RF, microwave, millimeter wave, terahertz or submillimeter wave. So when we are talking about the vacuum devices, what we meant for that, I am going to talk towards microwave ab millimeter wave. So we are going to talk in the range of 0.3 to 300 gigahertz. Coming to the next. So what we cannot think if microwave or millimeter wave is not there. So here in the 4 category I have divided. One is the civilian infrastructure and customer market. Second one is military. Third one is scientific and industrial. So civilian infrastructure and consumer market is quite well known. So common public knows this. So here we are covering TV, radio, satellite communication, our mobiles, then the radars, which is for public domain, it is available. For example, air traffic control, weather radar. Again, very important, that is the global positioning system, and domestic microwave cooking. These all we can cover under civilian infrastructure and consumer market. Coming to the military, the major requirement goes for radars, electronic countermeasure, and high power microwave devices. So in radar, here what we look for, it is a search radar, tracking radar, missile seekers, weather radar. Definitely the weather radar is applicable for military, slightly different than the weather radar which is being used for civilian infrastructure. Coming towards higher frequency side, then we talk about scientific, then plasma heating, then fusion energy research is going to be done with this millimeter wave range. Then charged particle accelerators are there, atmospheric radar is there, radio astronomy, medical field, all DNMR, NMR and all are being covered here. Then spectroscopy, all these studies of molecules and atoms are being studied in the scientific area using these microwave and millimeter waves. Then ground penetrating radars. Industry also plays a lot by these microwave and millimeter waves. So here we are seeing that testing and instrumentation, then material processing, industrial plasma, especially for semiconductor manufacturing. Coming towards the defense application, if you see the radar application, here I don't think I need to go through in detail. So what all I covered actually in the defense, actually search and rescue is the radar application. Actually left side you can see various radar applications have been put. So air traffic control, here actually it is a defense as well as civil application, both are covered. So I'll not go much in detail because actually our agenda is not towards the application, our agenda is towards the devices. Fine. However, actually I will be keep these slides available and my mail ID available for any clarification or any interaction. I will be always available for interaction. Fine. Now coming to when we are seeing these various devices and various applications. So what happened? It's always we can see in terms of frequency as well as average power. So in this particular slide, you can see the performance domain for vacuum, where we are covering fast and slow wave, both kind of devices, and solid state combined together. So in this, you can see whatever few lines are seen, so you can see one purple line is there, then one maroon line is there, and then bottom side you can see one green line is there. So these lines are basically the boundaries for various applications. So what we do, if you see the commercial application which is shown with brown boxes. So here all these commercial applications are there, like communication and telecommunication is there, commercial application based base stations are there, satellite communication is there, potential IVHS is there, then even LMDE which is going towards higher side. However, that also can be served with commercial application. Apart from that, you can see some blue various shapes are there. That is the basically domain where the military works, and the scientific area is shown by this pink color bounded by maroon color lines. So here actually if you see, these lines are the defining the boundaries. So slow wave vacuum amplifiers boundary line, when you are seeing it, you can see 10 to the power 6 means 1 megawatt of average power can be achieved with slow wave vacuum amplifier devices. However, when we are moving towards the higher frequency, if you see here, if you are going ahead than the 100 gigahertz, then you can see that whatever that average power requirement is there, that becomes limited. So here we can see, if we are increasing the frequency over the 100 gigahertz, then our average power level goes in only in kilowatt. However, when we are talking about the lower frequency, there we can even achieve 1 megawatt power and so. Fine. However, when we are talking about the fusion heating, which is required for generation of the plasma or fusion plasma, for magnetic confinement of fusion plasmas and all, so there that fusion heating is required. What happened exactly on sun? Like all these deuterium, these hydrogen atoms are joining for making deuterium, and then lots of energy gets generated. That kind of fusion reactors can be done, and even in France, that ITER program is there, that generally we call it sun on earth. So those kind of research, it is going close to 100 gigahertz. However, there the requirement is something like in terms of 1.2 megawatt. So that kind of study, that kind of this one devices can be done in the group of fast wave vacuum amplifiers or fast wave vacuum oscillators. A specific device which is gyrotron, that also we'll cover today in the lecture. Coming to the next, here we are seeing the peak power capabilities, like where I can use my solid state devices, or in market what all is available. So here we can see actually that whatever x-axis is all ordinate is there, here this particular graph is showing the average power, and the vertical axis is a peak power. And in between you can see some slanted lines are seen that basically talk about duty cycle of that particular device. So solid state devices are mostly being covered in some kilowatt energy and kilowatt of peak power and kilowatt of average power. However, when we are seeing the conventional microwave tubes, here we are talking about the average peak power of 100 megawatt, and the average power is between 10 kilowatt to 100 kilowatt. However, when we talk about high power microwave sources, here you can see that average power will be quite less. It is in the range of kilowatt. However, when we talk about the peak power level, here we are going to talk in between of 100 megawatt to 1 gigawatt. So still these research are on only. However, it's very limited places. And if you see only the 7 countries worldwide, they talk about HPM devices and sources. So basically these are being used for directed energy weaponry. Coming to the development cycle, so whatever these vacuum electronic devices are there, here the study starts with engineering design and material selection. It's quite important. I will be further coming what all technologies and engineerings are required for development of vacuum electronic devices. So first we do engineering design. In that one, the first role is there that RF design will be done, then electrical design will be done, then further mechanical design will be done. And then further we do the material selection, because it is not only one material the device can be generated, it will be number of materials are being used in one device for their specific requirement. So with that, the component fabrication will be done, and here the dimensional criticality becomes very tight, because whatever your frequency requirement is there, for that, like if number of devices, repeatability and all is required, so the metrology is very important, because all your dimension of the component should be within those tolerances. Then because these components are being developed, then it is required need to be clean. So chemical processing need to be done. Then film coating. Some of the places when we go with some material that cannot join with another material. So what we need to have one filler material, or some moment of time we need to have some kind of plating so that it will adhere with the second metal along with the filler material. So that chemical processing and film coating is required. Then further heat treatment and annealing. Here what happened, what all materials are being used that is of UHV grade, it is ultra high vacuum grade that is being used. However, because whatever these metals are there, they keep absorbing the atmosphere, or some unwanted gases will be absorbed. So heat treatment and annealing are required to pull those gases out, because otherwise this is a vacuum device, and when the electron beam flows inside, what happened, whatever these trapped gases are there, that comes out, and once it comes out, it makes the vacuum poor, and then electron movement will be disturbed. Then further, because all these components, heat treatment and all is done, then these components need to be joined. So then brazing, welding in protected atmosphere, because even these joints should be of ultra high vacuum grade material, because otherwise when the device is being operated, these gases will come out, it will make the vacuum poor, and device will not operate in the manner what way we look for. Then further, actually all these one, because actually you need to maintain the vacuum of the order of 10 to power minus 9 torr, that is the pressure level inside. So all the joint need to pass for that. So we do for vacuum leak check need to be there. Whenever any joint is being made, that need to be checked for vacuum leak. Then whatever this vacuum leak joints are there, putting all together, this vacuum envelope need to be made. So it will be either by TIG welding or by brazing. It need to be joined together. Then now this device is made, the vacuum envelope is now ready, need to be vacuum processed, because actually as I told you, whatever inside vacuum is there, that need to be maintained. So what happened, when we are operating the tube or operating any device, that particular moment of time, it should not start degassing, because initially when we pump it out, it will look it is a good. However, once the tube is energized, there is a possibility this electron beam hits on a surface and this trap gases come out. So we need to bake the tube at 550 degree temperature, so that whatever degassing is there, that will come within that tube, and it will be connected with the vacuum pumping system, where we pump out these gases, and once this vacuum processing is done, generally we pinch it off, and then inside hard vacuum will be maintained. Further, till now when we were talking, our vacuum envelope is only ready. Now, because all these electrons are there which is going to move inside the device, that need to be focused. Otherwise, it will be all are negatively charged, they will be keep repelling each other, and they will be keep on striking the wall, and will not get the movement of electron as per our desired requirement. So then magnetic fields are required to control them within the tube. Slightly we'll be going in detail when we are talking about the traveling wave tube. Then high voltage and RF testing is required, because here what happened, based on the frequency requirement, when we are talking about medium power level, then voltage ranges somewhere in 4 to 5 or 6 kV. So then again insulation and all is required, and that need to be checked. So what we do, first we do this high voltage test is required, so that whatever device is developed, that need to take these all high voltages. Then further, because RF testing is a device itself is RF device, then further RF testing will start. Further, because now so far it is only envelope is there, so it need to be rugged because it need to be fieldable device. So potting and packaging is required. Then further, because once we talk about defense devices, it need to undergo various critical environments. So these devices need to qualify for all the environment qualification. Here again, whatever this qualification is there, that is based on where this device is going for application. If it is naval application, accordingly the qualification test and all will be divided. If it is Air Force, then airworthiness need to be there. If it is a ground-based system, then ground-based environmental qualification will be required. And after this qualification is done, then only it is ready for delivery. Coming to the next, now we are talking about various technology and engineering drawn in design and development. So as I was explaining the development cycle, then you must have been seeing there is that high voltage need to be maintained. However, inside vacuum also need to be maintained. It means I cannot go with the metal envelope. It means in some part of that metal envelope, we need to have some ceramic because I need to maintain some high voltage between those two electrodes. So here the ceramic engineering becomes important. What kind of ceramic we need to use. So ceramic engineering is one of the field. Further, all these various chemical engineering concepts comes because what all that chemical cleaning and all, various chemical cleaning, even the vacuum processing, what all gases and all are being developed, how we need to pump out, those things comes under chemical engineering. Further, the chemistry we need to understand of the material. Computer engineering is required for the case of RF testing, automation, then further whatever simulation, then computer-based designs, their computer engineering plays into the role. Similarly, computer science is there. Then electrical engineering is required for all these electrical requirements because all these voltages, high voltages, power electronics, those all comes into picture. Definitely, once we are going to control the electron as per our wish, so electronics engineering comes into picture. Then energy science and engineering, because here all these electrons, they are going to carry some energy in the form of particle energy. Apart from that, whatever these RF is there, those are photonic energy is there. So that energy science and engineering becomes into picture. As I told you before delivery, we need to qualify for various environments. So environmental engineering comes into picture. And high voltage engineering is there because really various places, some of the places it will be low power devices, some of the places high voltage engineering is there that need to cater into. Then material science, because it's a various materials are being used for their specific requirements. Then mechanical engineering, because whatever the devices are there, various sections of the device going to give you different kind of heating. And then structural requirement comes because I cannot go for in general structure. So this structural engineering and thermal engineering also comes into picture. Even whatever this material is there, as I told you, actually it is UHV grade material. So metallurgical engineering becomes very important. So these are the various science and engineering which is being drawn in design and development of vacuum electronic devices. Coming to the other side, various technology and processes we are going to talk on. So computer aided design is there, then engineering design is being made, then thermal design need to be done. Then component fabrication is there, then thin film coating or plating is required for the purpose of joining to dissimilar material. Then in productive atmosphere, assembly will be made. Then in productive atmosphere, bracing will be done. And then ultra high vacuum need to be maintained. Then further what we do, in absence of electron beam, some of the tests we carry out, we generally call it cold test. And the beam present, a test will be done. That is called hot test. Then further packaging and then environmental test and qualification is the development part. Correct. Now we are going to, this slide shows various simulation softwares which is being used for design and development of vacuum electronic devices. So one is quite common, that is CST, Microwave Studio and Particle Studio, where we can simulate RF as well as electron beam. Then another software is there, that is high frequency structure simulator, where we can simulate RF, definitely not electron beam. Then another software is there, it's called Magic 3D, in which also we can simulate RF as well as beam. Then eGun is another software where electrostatic study can be done, and then electron beam can be simulated in that. Additionally, now we are seeing towards mechanical. So we are seeing here, there is one software, it's called SolidWorks, where structural and thermal simulation can be done. And this is another software where structural, thermal and magnetic kind of simulation done. Then FlowAFD, here what happened? Various places of the vacuum tube will be generating the heat, and we need to either by forced air we can cool, or we can do by liquid cooling. So here what happened, then the flow study, because how the air flows and what need to be channelized, those all becomes important, because we need to cool that particular section. So that there, that thermal as well as flow study can be done in FlowAFD. Then some specific software is there which is specifically for some specific tube, like this Sunray 1D and Sunray 2.5D is there, where large signal analysis of traveling wave tube can be done. Similarly, another software which is for gyro kind of devices, it is GyroK, where large signal analysis of gyro devices can be done. Then SURF3D, it is where that optical RF surfaces are being simulated, how the reflections happens of higher frequency waves, that can be studied. Another is there, that is linear optimization tool, there also that optical RF can be simulated. So these are the some typical software which the community use for design and development of vacuum electronic devices. Now here you can see, now we are going towards the agenda of today's lecture. So here in the left you can see there is written microwave tube. That is nothing but it is a vacuum electronic device. Now we are dividing into two, some oscillators and amplifier. In each category we are having slow wave device and fast wave device. So slow wave devices are those devices where the phase velocity of RF being altered, it is less than velocity of light. Those become slow. However, the fast wave devices, definitely, because when the beam wave interaction takes place, both velocities should be synchronous. And what happens when we are talking about the slow wave devices, definitely RF flows with velocity of light. However, particle, I cannot make it flow with velocity of light. Once it try to attain the velocity of light, it becomes wave. So then wave interaction is not possible. So what we do, generally we develop some structure, let it, what that RF phase velocity of change of electric field is there, that generally slows down, and then we will synchronize with the electron beam velocity. So that category called slow wave device, because here RF velocity, RF phase velocity of change of electric field is slower than velocity of light. However, in the fast wave devices, definitely here the question comes, in fast wave devices what you will do? Because here again, because if you are taking this fast wave devices, there the RF supported will be faster than velocity of light. What about electron beam? Here what we do, instead of making that velocity moving in straight, we make it to oscillate with the frequency, whatever with the required frequency. However, the phase velocity of that becomes higher than velocity of light. So those kind of devices comes under the category of fast wave devices. So in amplifier as well as in oscillator, both the categories, and in both the categories varies application. Here that some of the typical example has been put. However, it will be numerous number of devices is being developed worldwide. However, in this, for today's lecture, what we'll do in the slow wave device, we will take in the category of amplifier, we will be taking traveling wave tube. We will be taking helix traveling wave tube. And in the first wave category, we will be taking, in category of amplifier, we will be taking gyro traveling wave tube. In the category of oscillator and slow wave device, we will be taking magnetron. And in first wave category, we will be taking gyrotron. Okay, now we are moving towards today's agenda. So we are talking about slow wave device. We can call it conventional device because at least since long, whatever is being studied and work is continuously on, that is conventional devices, and mostly they are slow wave device. In that category, amplifier will be there and oscillator will be there. So first we will be trying to cover amplifier category where traveling wave tube will taken up. Later in, we will be going towards oscillator. There we will be talking about magnetron. Magnetron is a quite familiar device because it is being used in microwave ovens as an energy source. Okay, so here you can see there is one animation video towards down. Here you are seeing some electron beam is being generated from the electron gun and it is reaching up to one collector at the end at the right side. And here you can see there is one RF in and one RF out. So this is nothing but one amplifier, one small signal from RF in is being fed, and from that RF output, one amplified signal is coming out. Fine. So here we see how it happens. So there is an electron gun which will be responsible for generation of the electron beam. Here what happens when we go for beam wave interaction, definitely energies are conserved. So you cannot generate the energy. It means whatever your signal is being amplified, that need to take energy from somewhere and it has to come in the form of RF. So here in this particular device, what we do, basically whatever that energy of the electron beam is there, that is getting converted into the RF energy. So that way this RF is being amplified. Correct. Here for just for understanding, here on top you can see one assembly video is there. So I will run for, yes. So what you can see here, various components are there. Those are all of various different materials and how they assemble together to form a tube. So you can see actually this is that interaction region is being assembled now. Fine, that way it will be blocking. Again, that's gun and collector joins, then it will be placed in, and whatever the two couplers you are seeing, that will be, one will be for feeding RF in, another. So here you can see actually a typical example. If you see in particular tube, when we are talking about amplifier, the number of parts will be between 150 to 180. And the tolerances, whatever accuracy we look for this each piece part, that will be between 10 to 50 micrometer. And materials commonly used is oxygen-free, high conductivity copper, soft iron, OR, copper nickel alloy, molybdenum, tungsten, various ceramics. Then additionally, actually in this one, various like PTFE, Teflon, those are being used for beryllium copper. So actually it is just a typical example is given, whatever is being formed for the vacuum envelope. Okay, so in general, when we talk about a microwave tube, it will be having 5 sub-assemblies. There will be an electron gun, the second one is interaction structure, third one is the focusing structure, then fourth one is input-output coupler and collector. Even though it is shown under the category of amplifier, however, these 5 sub-assemblies will be always present in every vacuum electronic devices. Why? Because you need a beam wave interaction, you need to have some electron beam which will be giving its energy to RF. So electron generation is required. So we are having one electron gun. You can see on the center top one, we are having electron gun. Now, because you need to have a beam wave interaction, so which place beam wave interaction will take place, that is called interaction structure. Here only we talk about slow and fast wave. If the beam wave interaction is happening below velocity of light line, it will be slow wave interaction. When it is becoming at above the velocity of light line, it will be fast wave interaction structure. So here when we are talking about slow wave amplifier, here one of the interaction structure is seen. Here you can see actually there is one helical structure is seen. That is nothing but it is one of the slow structure. So what it do, it's basically slows down the phase velocity of change of electric field intensity. That's why it is called slow wave device. Now the focusing structure, we are going to focus our electron beam. So here you can see one structure is seen in the rightmost down corner. So here you can see S and N is represented. So here this is basically magnetic focusing structure which allows that electron to be focused and go in a linear fashion because it is for linear device or slow wave device. So over the axis, electron beam will be keep on moving in this structure. Coming to the structure, we call input-output coupler. So when we are talking about amplifier, I need to feed a signal which will get amplified and it will come out of the output coupler. Now the question comes, when we talk about oscillator, where will be the input coupler? Definitely, input coupler will not be there. So there is going to be only output coupler. That's why when we talk about the 5 sub-assemblies, input and output coupler, we put in one category. Now, because this beam wave interaction has happened, definitely it is not possible to convert all the energy of the electron beam which is propagating through slow structure. It will not be giving its full energy to RF. It will be still left with some energy. So that electron beam is called a spent electron beam. And that need to be suitably controlled. Otherwise, whatever these energetic beams are there, it will go here and there and it will spoil the device. So for that sake, it need to be collected at a structure which is called collector. So all these 5 assemblies should be always present in any vacuum tube. Correct? Here you can see some of the practical tube it is seen, how that one signal is being fed inside and how after amplifying it is coming out of the output coupler. Bottom side you can see it is a cut view of a helix traveling wave tube. So here again there is an electron beam, then focusing structure is there, and then RF in is being fed, and then from output coupler RF output is being taken and a spent electron beam is being collected at the collector. Okay, now we will be slowly talking about one of the other sub-assembly. So first we are talking about the electron gun. Here what is the situation? Here you can see one picture is there, where in the center there is a filament seen. So that here all these, there will be one another component is called cathode, and it is a thermionic cathode. So what happens, that back side of that one heater will be provided. So heater will be heating up that cathode, and because of thermionic emission, this will start emitting the electron. So emission of electron is not only the sufficient, because we want those electrons to move in the fashion so that the suitable beam wave interaction will take place. So accordingly, the structure will be whatever this in electron gun, we need to have some anode. So on top you can see some anode is seen. Then this is the cathode portion. In between, because we want to modulate that beam. So what we can do, we can have either beam focusing structure or control grid we may having, or shadow grid. So these grids are basically used for modulating. Either I can modulate the beam with beam focusing electrode or with grid. Then further anode is required because acceleration need to be given. However, in these devices there is a beauty. In the electron gun section itself, electron is being accelerated. Rest of the part, what happened, all these electron with its own kinetic energy, it is moving in vacuum. So after this electron gun, no accelerating structure is required. So after this section, full device can be put at ground potential. So handling that high voltages and all becomes easier. And at the end, on the depressed collector, on the end, we can go with the collector. However, when it is a depressed collector, I will tell you in further slides what is a depressed collector. So in that situation only, we need to have some high voltages, and then that section can be put at high voltages, then insulation and all becomes important there. So here you can see that some electron guns are shown. So that whatever that first structure is there, it is a BFE control. So you can see electron beams are being generated, and it is being linear beam. So here it is being generated from a spherical surface, and then because actually whatever the electron density is required in the electron beam, that need to be, because generation will not be having with that density, but we want a denser electron beam so that it will be having a high energy that can be transferred into RF. However, another structure down you can see, this is a BFE control. First one is the BFE control. In the down you can see instead of a continuous flow, there is a break in between. So what happened, actually this is a mesh kind of structure. These are basically called grids, and through that grids only this electron beam passes through, and then further it forms a linear beam. So this grid makes actually it helps us in modulating the electron beam. What I can do, when this electrons are being generated, I can give electron, generally cathodes are being put at negative potential, and if any higher potential is given on this grids, that electron start emitting. However, when I give further negative, whatever is below the cathode, I can stop that electron to move. So that way we are able to modulate the electron beam with this kind of either beam focusing electrode or with grids. Here actually just I want to make you people to appreciate. Here you can see there is a picture of electron gun. Then you can see that various material, whatever is going, actually here it is a assembly. Actually, if you see the total size of this particular electron beam, this is this particular electron gun is just an 1.5 inch size in length, and dia is 1 inch, and in that one various material is being used. You can see this various names are there. We have named various part. However, here I wanted to highlight the material. So here you can see stainless steel is there, then oxygen free high conductivity copper is there, then tantalum is there, alumina, ceramics are there because insulation is required, then coir material is there, then another structure is there which is of different shape, which is also made out of coir, then again cathode support which is made out of coir. Then whatever this seal ring is there, it is made out of stainless steel. Then another HV seal ring is there that is made out of coir. Then some sleeves are made out of molybdenum. Then whatever some ceramics are there which is of alumina. So here you will be able to appreciate one particular structure which is so tiny, which will be covering numbers of material. So that's why we call the technology, whatever is going, that various sciences and metallurgical science and all goes into this vacuum electronic devices. This is the another one. There also you can see various materials are being used in different shapes and sizes. And here again, because whatever the distance between cathode and anode is there, or cathode to BFE is there, that becomes very important. So those tolerances goes in terms of 50 to 100 micron. So actually this particular gun, whatever now you are seeing over the screen, that is also of 1.2 inch in length and 1 inch in dia. So in such a small structure, all these materials with very tight tolerances are being made for achieving a correct electron beam for going into slow structure for beam wave interaction. So here you can see one of the assembly is a cut view. Here also you can see that various material, otherwise all material will be having in the outlook, if you see, all the material will be looking similar. However, here you can be appreciating how the assembly is being made and how the closeness and all is there. And again, like if you see this shiny part, it is a BFE and this part is a cathode. You are seeing there is a small tiny gap is being maintained, and based on the requirement, this gap becomes important, because if for any reason if these two short, gun becomes useless because you will not be able to control your electron beam. Coming to the next. So now, so far we were talking about the electron gun, one of the subassembly. Now here we are going to talk about the second subassembly, which is a focusing structure. And in that one, a very specific focusing structure, it is periodic permanent magnet. So what happened, whatever these electrons are there, if I need to control, I'm having two way. Either I can control with electric field or I can control with magnetic field. So here generally, because if you have to control with electric field, you need to generate, because already accelerated, beam is already accelerated. So you need to control. And again, because I want to save my energy, I need not to again put one power supply for that. So what generally we do, we try to prefer some magnetic structure, so that over the axis, here you can see that down one picture is seen. So it is a magnet, then north pole and south pole is seen, and other side also. So it is a kind of a ring magnet, where there is another option, which is that with solenoid magnet, you are seeing that that right side topmost, you can see here that electron beam is being controlled with solenoid magnet. And definitely whatever this magnetic field is there, that should not go out, because again some peripheral will be there outside. So again it need to be magnetic shielded, so that whatever magnetic field is there, that should be available over the axis where electron beam need to move. So whatever I was talking about periodic permanent magnet, so that structure is shown here. You can see here number of magnets are there. Although it looks identical, however, when we see the field value, you are seeing here one arrow is going from north side to south side, and another one, it is going from north to south again. So what happens, this forms a period, Sn and S, then Sn. So this will form a period, that's why it is called periodic, and these magnets are permanent magnets, that's why it's a periodic permanent magnet structure. So here in this fashion, you can see that magnetic field is available over the axis. At this particular location, you can see it is in direction which is going from right to left. However, in this area, it is going left to right. So that way also you can justify, because first one is right to left, the second one is left to right, then again right to left, then again left to right. That makes a period. However, this helps us getting one axial magnetic field. So here what happened, when the electron beam is moving parallel to a magnetic field, it will not see any force. However, when it try to little move, or it try to make some angle, this magnetic field will start making it rotate. So what happened, because of that one, these electrons, whatever is trying to go out of the beam, it will again pull back to the structure, or in the main electron beam stream, it will join. So that way it focuses the electron beam. We call it focusing structure. Here that is specific focusing structure is there, that is periodic permanent magnet. Coming to the next. So here what happened, when this kind of thing, that PPM focusing is being used for traveling wave tube, particularly in case of traveling wave tube, mostly PPM focusing is being used, because actually it is a less in weight. There is no extra energy input is required, and no extra cooling need to be given, because this becomes smaller in size, and whatever structure is there, that will be putting in one base plate, and then base plate cooling will serve the purpose. So however, here what happened, that beam will be having criticality actually for developing this one, that beam will be keep on diverging and then converging because of this magnetic field. So beam will not be a parallel line. Here it will be forming one envelope which will be having some beam ripple. However, with this one, again, whatever that beam envelope is being formed, that should be within our requirement, because actually once this electron beam dia becomes bigger, it will start hitting that magnet. And once hits this, once the boundary is being hit, this energy of this electron beam will be going to that structure instead of reaching to the end and giving its energy to RF. Okay, then cooling of slow structure is being done for cooling this structure. Coming to the next, here again this ppm structure is there. So here that is stiffness competition for solid state is there definitely, because whatever these vacuum devices are there, they are continuously seize the competition with solid state devices. So that is there, then we need to have lesser weight devices. So that's why this ppm structure becomes important. Then requirement of tube with reduced size and weight, again same, because really that always nobody wants with heavy equipment or heavy devices to carry on. So that's why there will be always a requirement, okay, give me in a smaller size and a smaller weight. So because of that, this ppm structure is being used. However, the same amount of field, if you want to generate with one magnet, it will be approximately 40% higher than whatever you are going to use in ppm or permanent periodic component magnet. So basically for reducing size and weight, this ppm is being used. It gives better and optimum design. Then higher energy product magnets are being used. So the magnetic material which is being used in most of the tubes is samarium cobalt. So actually the two combination, this SmCO5 or SmCO17, and then this NdFeB. Actually this is the new material. However, still things are going on, because actually here that magnetic product value is not that high. So actually for stability and all, that is not being used. So the mostly samarium cobalt and samarium cobalt, these two combination is being used. So and further here actually for iron material, actually here what happened, when we talk about ppm focusing, so you can say actually if this material is there and it is being joined, definitely it is not being joined actually, even though it shows here with magnet it is joined, but it is not so, because whatever this structure is there that need to even create the vacuum. So in between some spacers will be put. So whatever this pole piece is there, it will be, these two will be joined, it will be separated by some spacers. That is will be generally of non-magnetic material, and therefore the field lines takes this shape, because actually if this is also a magnetic material, field lines will not be coming out, it will be a closed loop inside. Fine. So actually here like whatever that magnetic field, here you can see that one of the tube is there where this pole pieces are separated by spacers, and then these magnets have been put, and these are put in a different polarity as we see S and N, and then N and S has to come. So this need to be put. So now we know, because it is in different fashion, and then this they will try to repel it. So that's why you can see over the structure some clips are put. So that should be a non-magnetic material. So beryllium copper clips are being used to place the magnet in its position. So one magnetic field you can see here, and combined together as a stack, what is the magnetic field is done in that. So here you can see for one magnet, but the magnetic field goes in the range of something like 1100 or 1200 Gauss. However, when it is a combining, and then superposition principle take into role, so there the magnetic field peak values comes something like 2400 Gauss. So that way this magnetics is being used for focusing that electron beam. Now coming to the interaction structure, here we are talking about a slow wave interaction structure which is being used for helix traveling wave tube. So as I told you, there is a helix which is a slow structure. Now what happened, because this slow structure is over the axis, this need to be maintained. So what happened, again insulation need to be created from the barrel where this slow structure is inserted. So here you can see some yellow structure is there, that is basically boron nitride. Like we call it APBN, anisotropic pyrolytic boron nitride rods, which is a electrical insulator. However, whatever this helix is there that generates heat, this need to be transferred to the barrel, because actually cooling is only possible from outside. So whatever this APBN rod is there, that should conduct the heat, not the electrical power. So that will be having unidirectional thermal conductivity. So whatever heat generated over the helix through this one, it will be going to outer body. So here you can see that various structures and all, because various pole piece and spacers, and then this kind of barrel will be formed. And this is some techniques where how this is being made. And this is the structure after the stuffing, how the structure look like. Okay, so now this is that various dissimilar material which is joined with the filler material is shown in this plot, in this figure. Coming to the next, these are the various flow structure, like over the axis you can see helix is there and various support rods are being given. Some of the cases are for high broad bending, some cases for high power. So these are the various flow structures, pictures are shown. Now here, now the case comes how the beam wave interactions takes place. So for beam wave interaction, what generally we do, because whatever these electron beams are generating from the electron gun, it will be keep moving with a constant velocity. So what I need to have, because if it is keep on moving with a constant velocity, there will be no beam wave interaction. So what we need to do, we need to do first velocity modulate so that some bunches will be formed. So what happens? First is the velocity modulation, then it becomes density modulation. So here you can see there are 3 electrons shown in right side curve. One is A, R, and D. So here, whatever that electric field is there, that you can see it is a positive electric field. However, electron is negatively charged. So negatively charged and positive field will become, the energy itself will become negative, minus E of electronic charge, and electric field E, capital E, then minus small e, capital E will become the energy which is going to give you minus sign. So this electron, whatever is shown in yellow color, that will be decelerating. However, other side you are seeing some green color electron which is named as A. Here electric field is negative as well electron charge is negative. So two negative joining together will become positive. So it will be having the additional energy of small e multiplied by capital E. So these electron, whatever is in green color, it is being accelerated. So that's why this area is defined as accelerating field. And this particular half sign part is becoming decelerating. So what happened? Because it is decelerating, in the next cycle it will be left behind. And this green color electron, because it is accelerating, in the next cycle it will become further ahead. So in the down curve you can see they have come closer. So for each cycle, once it keep on moving, it will become closer and closer. And in the center, whatever red electron is there, that is neither seeing any positive field or negative field. So it will not be accelerated nor decelerated. It will be moving with whatever that constant velocity it has attained in the electron gun. So all these electrons will accumulate around this reference electron, which is neither accelerating nor decelerating. So what happens? This velocity modulation gets converted into density modulation. And as we know, if any charge is there, when it falls into decelerating field, it will radiate. So what happens when this bunch is being formed? After this, and now we know this is the decelerating area. What we do at that output coupler, we make synchronization in such a way so that this particular bunch falls under decelerating field, and then this bunch will give its energy to RF. Then whatever input signal is there, that will get amplified, and we take that signal out from output coupler. So this is the basic mechanism of beam wave interaction. Then further coming to the input output coupler, coupler is also one of the very critical assembly. Here what happened? See, inside the tube you need to maintain the vacuum. However, outside atmosphere is there. So we want a seal for atmosphere not to enter into the device. However, from the same path we want RF to come out. So one end we want to stop atmosphere and RF to come out. So it should be a good seal for vacuum and atmosphere, and it should be open for RF. So this is one of the typical window means coupler window, as well as this impedance transformer is planned, because inside the tube, there will be a helix which will be having impedance varying with frequency. However, outside, you need to use your, for output atmosphere use, you will be using some cabling. It will be either 75 ohm line or it will be a 50 ohm line. So impedance match is required, then only that maximum power transfer will happen. So here in these couplers, we will be having one RF window. Is that ceramic you can see here. The ceramic is nothing but window. Then it is a coaxial coupler design. So inside the device, you are having a helix. It is being coupled with 50 ohm line. So, and then further, because when it is input, your signal is very less. So you can bear with one small structure, and then because low power handling is required. However, when the power becomes more, you need to handle a big amount of power. So output connector size will become bigger. Correct. So now further, as I was telling you actually that further in the slide, I will be talking of collector. So here you can see that electron beam is being generated at left end, and after passing through this flow structure or helical structure, it is being collected. So what happens if the amount, if the with full energy, if it hits this collector, big amount of heating will be generated. So as I told you here, up to gun section, only acceleration is happening. In the rest of the area, it is moving with its own kinetic energy. So whatever this kinetic energy is there, after reaching to the collector, if it is at ground potential, that much energy will be simply waste, because it will go and hit the collector and it will be generating heating. So what generally we do, actually up to the area where beam attraction is taking place, electron beam is of my use. After that, it becomes a dump over the collector. Just suppose if I am able to decelerate in this collector, this electron, then it will be hitting with lesser energy, and then amount of wastage of energy will be saved. So for that purpose, we use a depressed collector. So what happens? It will be put, it is being put at some negative potential, so that whatever electron entering into the collector, that will become slows down. That's why we call it depressed collector. Then further, actually, whatever these depressed collectors are there, they are in different stages. Like I can slow down in a different fashion, so that maximum energy I can recover out of that. So here you can see actually this is, if it is a single stage, this area whatever is shown in black, this much area only can be recovered. However, when it becomes a multi-stage, you can see additional area whatever is further being covered, that energy also can be recovered in a multi-stage depressed collector. So this kind of possibility only is there in tube. This kind of thing cannot be done in any solid state devices. So energy recovery is also possible, that makes the device more efficient. Alright, so this is that it is some comparison being made when it is a single stage collector. It will be going to give you 45 to 55% efficiency. However, when we are talking about multi-stage, it is going to give 60 to 80% efficiency. And then overall device efficiency here, it is in single stage, it is 15 to 20%. However, in multi-stage case, it becomes 25 to 30. And then power dissipation, I have already told you, because here power dissipation will be more, and in multi-stage power dissipation will be less. So here various combination is being tried, like different stages are there. Here you can see these are the 4 stages. 4 stages, actually all different stages will be collecting the electron beam in a different fashion. So accordingly that energy recovery will be happening. So here you can see, this is one picture that how the electron beam comes and being collected at different stages of collector. So electron beam is entering from the left side, and it is being collected at different stages shown in blue, red and green color. So this is the concept of multi-stage collector. Now coming to the oscillator of, actually that much was there for helix traveling wave tube. Now I am coming for the oscillator. So first one was amplifier. Now coming to the oscillator, I am seeing that I may run out of time. So what we'll do, slightly we'll be going faster now. So whatever this magnetron is there, it is all household ovens. They will be having the magnetron. So here that electron beam, here this is the structure. In the center, there will be a cathode, and outside there is a anode, which will be having various resonant cavity that is going to define the frequency, whatever is being generated in this particular oscillator. And here, right hand side, you can see some loop is there. So whatever energy is being generated, that is being collected, means it will be coupled to outside world through this pickup loop. Fine. So here various different kind of cavities are being used for their here. However, the most common which is there, that is A6 vein, that is the most popular. However, other structures having their own positive and negative. However, that particularly for the defense purpose and for the scientific environment, A6 magnetron is most common. And whatever we use in domestic magnetron, there, because really fabrication of this vein kind of structure is easier. So domestic magnetron uses this vein kind of structure of cavity. Okay, so here what happened, in the center you can see there is a cathode, then electrons are being generated. If, just suppose if magnetic field is not there, so what will happen? These are the field lines. So electron beam is generated from the cathode, and then directly it will go and hit the anode. Whatever that outer periphery is the anode, so electron beam will hit. So here we are not going to get any benefit. What we need let this electron move in this area for a longer time. Then only the beam interaction will take place for a bigger time. And whatever that energy transfer is there from this electron energy to RF, that only comes as a generation of that RF, which we can couple to the outside world. Now, coming to the bottom picture, here you can see there is another structure where magnetic field is present. So whatever these plus symbols are there, that is showing the magnetic field going down towards this inside the screen. So when this electron beam is being generated from the cathode, and it is having a, see, whatever all these electrons are there, they are having a tendency of generation of from the cathode perpendicular to the surface. So electron beam is being generated from this surface and it is trying to go straight, but because this magnetic field is there, and then this Lorentz force will be applied, and then it will try to turn towards one. So earlier in this situation, it was trying to go straight. However, here when I am able to make it turn, it means I am giving it longer path to be there in this free space area where beam wave interaction will take place. Correct. Now here you can see in this cavity structure, three situations are there. When the magnetic field is 0, then this blue line will be followed, a straight electron will go and hit that anode. Then green path is there when with a critical, actually if magnetic field is lesser than a critical value, it will take a small curvature and it will hit that anode. Now coming to the next situation, when this electron are having a whatever that magnetic field is there, it is exactly same as one critical magnetic field, that generally we call it that Brillouin field. If it is so, then it will be following that red path. So that becomes slightly longer. And just suppose if further you are going ahead, so what will happen? This curvature will become very short and it will be keep hitting the anode itself, cathode itself. It will be generating from the cathode, again it will hit, then again it will generate and hit. So our requirement, we always look for a critical magnetic field so that we should get this red path for beam wave interaction. So here we are seeing actually two curves are there, two conditions are there. Here one red curve is there, it is called, actually it is a voltage versus magnetic field. So this is called Hull cutoff. It is because whatever that first magnetron, it was developed by H.U. Hull. So this is the theory developed by Hull only. So that's why it's called Hull cutoff. And another one is there, this is blue line, it is Goodman-Hardy condition. However, the device operates between these two lines. So when we select a voltage, then this curve is seen. So the operation will be between this one. So magnetic field accordingly need to be selected. So generally in the center of this one, that magnetic field will be selected so that oscillation will occur. Below that, it will be directly conducting, so electron beam will go and hit. Above that, cutoff will happen, electron beam will again come back to the cathode. Correct. Okay. Okay, this I will explain in the next slide itself. So here you can see actually that various modes of operation is there. So here you can see actually generally magnetometers is being operated in pi mode and 2pi mode. So here you can see actually these lines, these arrow lines are seeing left side. However, next one is seeing other way. So this, because actually 180-degree phase shift is there between two cavity. That's why it is called pi mode operation. However, in another case where the 2pi operation is there, see all the cavities sees the same kind of electric field. So that is a 2pi operation. Here again, the same way we are explaining whatever that electron beam is moving, because whatever that outside cavity is there, and because it is RF signal is there, so positive to negative. So in one case, when it is positive, electron will be seeing decelerating situation. However, in this one, when negative is there, it will be seeing acceleration. So here, when the electron are decelerated, it gives energy to the field, and then signal will be amplified. Other case, when we are seeing the electron accelerated, then electron will acquire the energy from field, and then field will reduce. However, our requirement is there, let that whatever these electrons are there, let them be decelerated so that it will give this energy. So whatever that noise is there, that will be amplified and that can be taken out for application purpose. Okay, so here, because whatever that path of the electron is there, I will explain in this video. You can see there some electrons are being generated at the cathode, and initial stage, you can see above the time is there actually around 4 to 5 nanosecond time. This electron beam with a given magnetic field, it is for pi mode. So you can see here that this is A6 magnetron, so 6 veins are there, and now you see that spokes are formed. So whatever these spokes forms, these spokes will be also not stable. You will see this spoke, because RF is there, it will be keep rotating there, and then these spokes, what all these electrons are there, it is being decelerated and it's keep giving energy to the this cavity, and then through one of the cavity we can extract that power. So this slide shows 4 different kind of coupling mechanism. So first one is there where the segment itself will be put with the center conductor, and one ground connection will be made. So with that coaxial line we can take it out. Another coupling mechanism is the loop coupling. So whatever these cavities are formed, in that one loop will be made. Out of that one, energy will be coupled out. Similarly, that strap fit is there, because here alternate cavities are being strapped with strapping. Through that also we can take the power out. And another option is there, that slot coupling. Through that we can extract the power. Okay, so this is towards slow wave side. Now we are moving toward the another one, that is a new generation that fast wave devices. So here in the category of oscillator, we will take gyrotron, and in category of amplifier, we will take gyro traveling wave tube. Definitely we call it new generation because really whatever so far worldwide researches are going on is mostly on slow wave devices. However, few countries are working towards these fast wave devices, particularly in the scientific area. Actually, a few commercial applications are also there, but that developed country only have so like they are using gyrotron for material processing and all. So coming to the gyrotron, why we go for? Let us understand why we go for these devices. So what happened now? You have seen whatever the slow wave devices I have called upon. Once their frequency goes higher, their cross-sectional dimension comes down. When you are going for higher and higher frequency, for example, I will tell you actually if you are working for KU band, so helix ID becomes less than 2 mm. Then further frequency when we go higher, it will become further narrowed down. And again, this electron beam need to pass through that structure. That becomes always difficult because this electron beam will hit that helix. So for conventional microwave tube, The problem is this DC power dissipation starts, RF losses, because that whatever that surface is there, that itself will whatever this RF need to flow, that itself loses its energy. So that becomes RF losses. Then again, because whatever that electron beam is there, that I further need to bring it down in radius. It means whatever attenuable electron current density is there, that is also having its own limitation, because all these electrons are negatively charged. They will be trying to repel each other. I cannot bring it to 0 dimension. Similarly, because whatever this heating and all happens for a smaller structure, it is very difficult to drain out the heat. Then a smaller structure, material arcing happens. So material breakdown problem comes, and again, very difficult to make these tiny parts. So that is when we are seeing the conventional device and we are trying to increase its frequency. Other side, we are already having lasers. So what I can do, lasers in optical range. I need to reduce the wave frequency to coming into microwave and millimeter wave range or sub-millimeter wave range. Once we are coming, each quantum will be having each quanta, because now we are reducing the frequency, and h nu is the total energy. So because each quantum frequency itself has reduced, so the total energy reduced. Apart from that, when we are talking about millimeter and sub-millimeter wave range, it's very difficult to sustain the population inversion, which is required for making laser, generation of laser. So there is the solution required. So what we do, whatever these gyro devices is there, they are trying to fill the gap. So here you can see left side, bottom axis is wavelength and vertical axis is average power. So lasers are available when we are talking about lower wavelength, and conventional power tubes are available for higher frequency. In between there is a gap. So these gap, generally we call it technology gap. That filling job is possible with these gyro devices or fast wave devices. So the average power capability, if you see here in this graph, actually here we are seeing that average power left side, and then year of development is bottom side. So here you can see whatever Zytron device we are talking, that this brown curve which is coming with within that red oval shape is here. So one general common question comes, whatever this yellow line is further better, and that is for free electron laser. So that is further better. Why you are appreciating, why you are going with this device? You can go with free electron laser. So the answer is, here you can see, when average power is seen with frequency. So Zytron is somewhere here. You can see with this red circle, Zytron is seen. However, you can see this rightmost edge, free electron laser is seen. So when you are talking about higher frequency and higher power, here you can see Zytron is available up to megawatts of power, and frequency is close to 100 gigahertz and around. So higher frequency and higher power is achievable in Zytron. However, when we are talking about free electron lasers, they can give you a very high frequency. However, their power is limited only by kilowatt. So that's why for scientific research and all, always particularly for plasma fusion and all, Zytrons are preferred. So this is the device which we call it Zytron. You can appreciate, because there is no input coupler, there is only one output coupler. So this is an oscillator, and the signal comes out from one of the window. It's output coupler, it is coming out. So here you can see, actually this is the area, actually here this is a cavity area where the beam wave interactions takes place. So this is the electron gun which will be generating helical electron beam. So you can see these are the helical electron beam is being generated. Then it comes into this central cavity area where RF signal. Here one interesting thing you can see, even though signal is being generated here, however it is not moving towards left, it is only moving towards right. What happens, whatever this generation is there, we always want not to go towards gun, because otherwise beam wave interaction will start in this gun area itself. So we taper down, and we know once the radius of the waveguide becomes lesser, cutoff frequency of that waveguide becomes higher. So whatever the signal is being generated for, because of this down taper, it becomes cutoff area. So whatever that RF signal is there, it is not being allowed to go towards that, and in that line my electron gun will not be disturbed. However, we need to pull this energy out for our application, so it goes out. So then further in this one, whatever this energy is generated, I want to separate it out of the window. So in between there will be a launcher and mirror structures. So phase correction and all will be doing inside this area, because here it is a cavity mode. However, whatever we need to propagate in air, definitely that waveguide modes are not possible to be propagated in air. So we convert into Gaussian beam. Then Gaussian beam can comfortably being radiated in atmosphere. So here that mode conversion from cavity mode to Gaussian mode, it will be converted, and then there will be a phase correction mirrors. You can see some reflections are seen, and then from this output window it will be taken out. Okay, so actually this particular one will be having number of sub-assemblies. So we are having magnetron injection gun, which will be responsible for generating the electron beam. Then there is a beam tunnel, because we don't want that RF to come up to the gun. So this is structure, and even because this is cylindrical structure, there is always possibility whatever noise is available there itself, that beam wave interaction will start. However, this is not the area where beam wave interaction should happen. So that's why in between one structure is being put, which should stop all the oscillation created in that area. So that's why it is a ceramic and metal structure. It's called beam tunnel. Then interaction cavity is there, where beam wave interaction will take place. You will be surprised to know, actually, whatever this interaction cavity is there, if you see the total volume of the device, it will be hardly 1% of that volume. So interaction cavity is 1% of the total volume. However, this is only responsible for full beam wave generation. So all this energy is being generated in 1% volume of the total device. Then further, this nonlinear taper is there, because you need through this nonlinear taper, because energy is generated in a very small volume. Now, because actually you cannot have the energy in that small volume, so you need to make now this volume bigger. However, you are not being allowed to reflect any amount of energy, because again it will be generating the heat. Then this mode launcher is there, which will be converting your cavity mode into the Gaussian beam, and then mirror section where the phase correction takes place. Then one RF window is there, through that it will come out. Here the requirement of magnetic field is very high. For each 28 gigahertz, the magnetic field requirement is 1 Tesla. So just suppose if you are working for 95 gigahertz and all, there it goes in 3.65 or 4 Tesla requirement. Then at the end, similar to the other microwave tubes, there will be a collector which will be collecting the spent electron beam. So here again, for fast tube device, I will try to explain that how this, as I told you, in case of helix traveling wave tube, there should be a velocity modulation that will get converted into density modulation, and then this density modulated whatever charges are there that need to be put in decelerating mode, so that it will give its energy to RF. So similar kind of situation happens here. Here again, because these electron beams are helical electron beam. Here you can see, actually in these plots you can see these electron beams are moving helically because of high magnetic field. So I can take 3 electrons, 1 electron red, green and yellow. My electric field lines are in this line. Actually you can appreciate here, it will be like this. However, it formed in this simplified manner, it has been shown here. So this electric field in this direction, and electron movement is perpendicular to the electric field. Because electric field is perpendicular and electron movement is this direction, this will not see any energy increase or decrease. So it becomes a reference electron, which is in red color. Now take this electron. This electron is a negatively charged. It is moving in this direction. So it is having tendency of going up. So it is a negatively charged. It is seeing positive field, and it is moving also in the same direction. So because electric field and electrons are in one direction, so what will happen? Its energy will reduce, because it is minus E and capital E. So it is negative. So it is energy is reducing. So when energy reduces, that relativistic mass factor decreases. And it is a simple formula of cyclotron frequency. When here this gamma, the relativistic mass factor decreases, definitely your omega C is going to increase. So omega C is increasing, and that cycle for completing one full cycle, that is cyclotron time for completing that cycle, will decrease because omega has increased. In lesser time it need to complete the full circle, so time period is decreasing. So now because this time period has decreased, now I will just try you to appreciate whatever this electron is there, it has reduced its energy or it is decelerating, but time period has decreased. So it has reduced its energy and time period has reduced. It means it will be start moving faster. It is a contradictory statement because this is having less energy, however it is moving faster. So this will have a tendency to move little ahead in the next cycle. In the same fashion, whatever that another electron is there, which is getting energy, but will become slow down. It will come slightly behind as shown here. So this way, the velocity modulation will happen. And then because this all will come closer to a central electron, which is neither accelerating nor decelerating. So bunch will be formed around that. So density modulation will happen. So now we know this side is all decelerating. So what happened here, whatever this bunch is there, at where we are going to take that energy extraction out, we move this bunch into decelerating phase where this will radiate and its energy will get converted into RF, and that we take out from this oscillator. So this is the various piece parts shown for the gyrotron which we have developed at MTRDC. So you can see actually this is various part. This is the HV seal. This is the anode structure. Here there is a strip cathode. This is window. This is some mirror box. Then this is window box. Here is the beam tunnel. Then this is beam tunnel to cavity assembly. Then this is cavity. Then launcher. This you can see inside how this beam tunnel is joining with cavity, and then this is the launcher, and then mirror structures are there for reflecting that RF signal generated inside and getting it converted into Gaussian beam, and then further phase correction will happen. And at the end, there will be a collector. And here you can see in between, as I was telling you, because actually I want to use the concept of depressed collector, there should be insulation required. So this is the isolation ceramic, which will be allowing me to put this collector at different potential than the structure. So this is the depressed collector concept is even used in gyrotron. So this is the gyrotron developed by MTRDC. Here you can see, you may be able to appreciate, actually it was for 90, actually this was supposed to give a spot frequency between 94 to 95. And here you can see actually one peak in this spectrum analyzer. You can see there is a peak available here, which is at 94.04 gigahertz. This is the recent development at MTRDC. So this is the device which is being developed, and as a high magnetic field is required. So you can see this is a big magnet being put. This side is the electron gun. This is the window. Out of that one, that power will be coming, and this is the cooling channel with that one, because collector will be getting heated up, so that will be being cooled. And always we use, as I told you, that is a good vacuum need to be maintained. So this is the ion pump, which will be keep evacuating this device for maintaining it high vacuum. Okay, now coming to the fast wave amplifier side. So here we can see the structure. If you see from oscillator to amplifier, the previous one was gyrotron, which one an oscillator, and that another one is gyro traveling wave tube, which is an amplifier. So here you can see rest of the structure becomes all the same. However, here we have introduced one input coupler. So in further slide, I will try to justify that. So this input coupler is getting some small signal and it is getting amplified. And here the window here actually, because we don't want it to have the transfer output. That's why actually whatever is there, that waveguide mode itself, we are extracting here. Because actually still whatever these gyro TWTs and all are there, those are developed up to kilowatt level. It has not seen the megawatt and gigawatt situation. So this one will be in cavity mode itself. It is being taken out, and then whatever that mode conversion and all is required, that is being done by outside mode converter. So here you can see actually whatever that input signal is being fed from this input coupler, it is going in the intersection, and the same concept, whatever that energy is being entered, that should not go towards gun. So here you can see again one down tapper is given, so that energy is not going that side, and all the energy is propagating in left to right side. And again you can see whatever that signal is going, the further towards the end, you are seeing that intensity is becoming this blue and yellow. So whatever energy is going, it is at different stages, it is being keep amplified, and at the end of the device where output coupler is being placed, amplified signal you can see that is there. Okay, so this is some wrap and round coupler which is made for 35 gigahertz gyro travel.
I think Mike has been muted.
I think he has network issues on his end. The video is stuck. Sir, can you please talk to the speaker, confirm from his end? Okay, he will be joining again.
Yes, ma'am.
Okay.
We should wait for 2 to 4 minutes, ma'am.
Sure.
Yes, I request the participant to please wait for 4 minutes, 2 to 4 minutes. Our speaker is soon trying to join the session.
Okay, sir.
Again, I humbly request the audience to please wait for 2 to 3 minutes. He is trying to connect.
Slides. Am I audible to people?
Yes, yes, sir. We can hear you.
Yes, sir. We can hear you.
Okay, fine. I am extremely sorry for this disconnection network issues.
No problem.
No issue. Yeah.
Okay, fine. So actually, as I was talking about this gyro traveling wave tube, here actually we are seeing some input coupler is required, which signal will be amplified and it will be taken out of the output coupler. Coming to the next, this I think this I have explained and people could get my point. So in this one, actually, whatever that input signal is being fed from the input port, it is getting in all this traveling. After all this traveling, in the end, you can see the amplified signals where the field intensity, you can see it is a higher side field intensity. After this amplification, we take this signal out. So here, actually, some of the couplers you can see. So here, what happens? When we are looking for a higher order mode beam wave interaction, so from this port, this is the input port where TE10 mode of rectangular waveguide is being fed. Then it is getting converted into a wraparound structure, and in the center there is another structure where the signal is being fed. So what happened? This particular TE10 of rectangular waveguide is being converted into TE01 of circular waveguide. So here you can see from this port, it is TE10 of rectangular, and this is the port where beam wave interaction is going to take place. That is TE01 mode of circular waveguide is there. So this is one of the coupler which is designed for one gyro traveling wave tube. Further, for the further higher order mode, again same TE10 of rectangular waveguide is being converted of TE02 of circular waveguide. So you can see at the output port, here you can see in this one, there is a one ring, one maxima ring is seen. However, in the second one, you can see there is two ring. So because it is azimuthally symmetric, so that's why that first number is 0. And the second one is there because in radial direction, once you move, you are seeing two peaks. So two half sinusoidal variation is seen. So that's why 0-2 mode. However, in this case, it is only one. So it is T01 mode of circular waveguide. Fine. Here we are talking about the dispersion characteristic of gyro durability. And this is one of the gyro durability is developed by China. It is at 35 gigahertz. That University of Electronics Science and Technology of China, Chengdu, has developed. So this is the device. Actually, for this one, you can see the total height is something like 12 feet, including whatever that base side, whatever that magnetron injection gun, oil tank and all is put. So with that one, you can compare how this new generation device size becomes bigger, and accordingly need to be decided. However, here also, as I told you, in gyrotron, it is approximately 1% of the section, volume section, which is generating the full energy. However, in gyro tubes, that section is a longer length because we need to have the traveling wave interaction that will be slightly longer. However, that other peripherals, whatever, if you see when you are going for higher frequency, your requirement becomes, as I told you, in case of gyrotron, 28 gigahertz looks for 1 Tesla. The requirement of magnetic field is similar in gyro tubes also. Okay, as my time is up, we will be closing here. Actually, even whatever my agenda was there, so that we have covered in slow wave regime or conventional side. We have covered one oscillator, which is magnetron. In amplifier, that is a traveling wave tube. Coming to the unconventional or fast wave device, we have covered in amplifier, we have covered gyro traveling wave tube, and in oscillator, we have covered gyrotron. Actually, I wanted to give some glimpse of hybrid devices, but my time is up. So we are going away. Anyway, actually, we will be further planning some moment of time. Actually, I wanted to give a glimpse of the problem, whatever solid state and these vacuum devices have. and how the solid state, putting the solid state down, this vacuum devices come up. Because what happened, as Professor Satyen Sharma also told, because still people are having a feeling of that vacuum devices are obsolete, and it was done while Second World War of 1940s. So I wanted to give some glimpse that how this solid state device actually, solid state devices are there. Definitely that GaN devices are developed, and then they can handle a better thermal. However, still it is not comparable with vacuum devices and what all vacuum devices could give. So I was having the idea that I will, towards the end, I will be talking about a hybrid device which is called microwave power module. Anyway, that we will be putting for some other time.
Also, you can discuss another 5 minutes. You can briefly, if you want to give a glimpse with a slide.
What I will do, actually, the idea was there. So one particular slide I will take you, that where what happened. Actually the continuously fight was there between solid state people and vacuum people. Always it was being told, I am best, and we will be countering each other. That kind of thing was going on. So what happened, actually, there was one tale I will tell you. This tale, you can see, it is quite interesting. What happened, actually, like here you can see, it's old era where tube is being developed and then it is being examined by one person. So earlier there was a problem with tube. People were trying to dig out, by research, trying to improve it off. Similarly, at a later stage, this one, that solid state devices are also being developed. So however, that solid state devices were also having the issue. So here we correlate with our society. That tube was becoming, actually with research, tube become a glamorous lady. However, the solid state device becomes a handsome man. So once they come up at a stage where the plan was there, why not to take benefit of all? So they joined together, and then this marriage happened between the two. And then there was a generation of a new device, is called microwave power module. So this small kid you are seeing, where on this, it is shown as...
So your screen is not moving, sir. It's freezed.
Okay. So actually what I will do, whatever that ninth corner is there, in that one you can see there is a kid which is Ampium. So what happened, this particular technology has come up as a hybrid device, which is taking as the benefit of solid state devices as well as...
So we are able to see your screen, which is mentioning a typical gyro traveling wave tube.
Oh, it's not moving.
Yes, sir.
Now?
Now it's moving, sir.
Okay, sorry. So actually, I will be talking somewhere here then. Okay, just give me 2 minutes of time so that I can talk on this. Okay, so there was solid state device as well as vacuum electronic devices. So continuously fight was there. Solid state people were telling, oh, younger is superior. And then vacuum people were telling, old is gold. So that human psychology is there. Okay, younger is superior. As generally human psychology goes in that line. So, okay, we will skip that one. This also we will skip it off. So there was a fight. Then why to fight? Better to shake hand and move further. So in that process, the solid state devices and the traveling wave tube devices have joined together, and then one new device came into picture. It is microwave power module. So I will tell you about the superiority of this device. If you see, here we are comparing Ampium versus TWTs, or Ampium versus vacuum devices, and Ampium versus solid state power amplifiers. So for size, it is Ampium will be 5 times smaller than for the same power level if TWTs are there. And other side, from SSP, it will be 8 times smaller. Weight wise, as volume is going by 5 times and 8 times, weight wise also it will be 5 times and 8 times smaller. Noise wise, much improved. It will be MPMs are much better. However, towards the SSPA, it will be 2 dB degradation is reported. And efficiency wise, differently, because it is using a concept of gain sharing between solid state and vacuum devices. So here efficiency improvement is there because it is a depressed collector as being used for tube, and some planar transformer and all is being used for electronic power conditioner side. So that efficiency wise, from solid state, it is 3 times better. And here 50% improvement in efficiency can be achieved. So this is the device what I was talking about, MPM. Actually, this is the device generally, means at present I am developing on. So it is a kind of my own baby. So I enjoy doing that. So here you can see that various sections of that. So here we are having traveling wave tube, we are having that planar transformer, then heater power supply need to have, then housekeeping power supply is there. Then this solid state power amplifiers are there. They are all sitting together in one small chassis. It will be very compactly put. And then this device is called microwave power module. So these will be having various application in electronic warfare, satellite data link, command and guidance, then synthetic aperture radar, then even missile seeker, towed decoy. These devices, because of its all beauty, see here we are using vacuum tube as well as solid state. However, this come up with a better result. So that is there. Actually, here is some of the product which MKDC, my establishment, has developed. So some of the MPM for various applications it is being developed. So like this is the MPM which is developed for LoRa system. This is developed for Sarvagya NW system. This is for flight labeling radar. This is for TLR troop label radar. It is developed. Then here this is developed for Akash missile. This is developed for Rustam satellite data link system. This is for Sarvagya EW system. So these are the some of the devices which is developed. And here we are comparing with like 3 category of units are there, where we are having a marriage of solid state devices as well as vacuum devices. So one is called traveling wave tube amplifier, the second one is microwave power module, and the third one is transmitter. So how we distinguish these one? So MPM is a device where mini tube, a power supply, and solid state power amplifier is being used with the concept of gain sharing, so that this MPM comes into picture. However, when we are talking about traveling wave tube amplifier, here solid state amplifier will not be there. So it is like a conventional tube, and high voltage power supply will be there, and sometime input and output components are being put for giving high power. So that is traveling wave tube amplifier. However, when we talk about transmitter, here there will be a power amplifier that may be of conventional tube or mini tube, and then power distribution is required. So it will be a different kind of electronic power conditioner. Then RF components are must in transmitter. Then there should be a command and control. Then cooling is also a necessary part of transmitter. So with that, I will try to conclude. So these pictures are showing the book published by me and one of my co-author, Professor B.N. Basu. So actually, this is the book which is by me and Professor B.N. Basu, and these are the book one which is written for in Hindi.
Again, we are not able to see the slide. I mean, slide is stuck.
At which slide you are?
Younger is superior and old is gold. Yes, now it is moving. Yes, we can see the book now.
Okay, so I was talking about this book.
Yes.
You were able to see that high power microwave?
Yes, yes, now we can see.
Okay, fine. So actually, okay, so
we can see. we can see.
Okay, fine. So actually, this is one of the book which is co-authored with Professor B.N. Basu. He is the retired professor at Banaras Hind University Institute of Technology by that time. Now it is Indian Institute of Technology. And this was the another book on this one, Gyro Traveling Wave Tube towards the interaction structure. And this is the book which is written in Hindi. So with that, I would like to thank all the participants as well as organizer for paying their attention. And sorry, in between, actually at my end, there was a issue at network, and there was some interruption in the full sequence. Now session, I can open it for question answer. So I'm available for question answer.
Okay, sir. Thank you, sir. Now we are open to the question answers, and we do have received a few questions in the chat box. The first is from Mr. Ganga Sagar Verma, that which type of software is used to design these devices?
See, actually here, what all these numerical methods are there, on all some softwares have been developed. Like when we see that whatever with method of movement, then you are having FEM, FTDM. So all these are the general kind of software. Additionally, whatever multi-physics bit softwares are there, those are also being developed. So like whatever that one series of software I have shown, so in the start you may be seeing like HFSS is there, that is FEM based software. Similarly, whatever that ANSYS is there, that is also FEM based software. However, when we are talking about Cert3D, LOT, Sunray 1D and 2D, then GyroK, those are multi-physics based software. Similarly, when we are talking about when structural and thermal simulation we are talking, there also that FEM based softwares are quite popular. But what happened, when we are using multi-physics based software, it is doing a dedicated job based on our requirement. However, when these numerical methods based softwares are there, they generally talk about general software, so that various kind of models can be done there, that complicated structure and all can be used, but definitely they are going to take huge time. So that's why generally we prefer whatever physics based software is there, so that actually whatever our process cycle and iterations are there, that will become much faster. Otherwise, for example, I will tell you, if anybody is trying to simulate a helix TWT with a conventional software, like if CST, if somebody is trying where that beam as well as RF simulation, both are possible. In that case, what happens, it takes more than a month for doing one device iteration. And if any alteration in any dimension, if you are doing, that will be optimization itself goes months together. So what we generally do, we develop our own software, a kind of numerical, basically it's a physics-based software, so that in this one, first we try to optimize all the parameter, and for a final run where the whole device can be put together and can be simulated, that generally we do in this CST kind of software, where the beam wave interaction. Similarly, whatever another is there, that is Magic 3D, there also that RF and beam both is possible. Full device can be done, but again in that one also, even though it is a multi-physics software, but what happened, it do lots of work which is not required to me. So those kind of general software, definitely it is going to take huge time, and then again, whatever that computational facility and all, there you need to have more. Another question?
The next question is from the same participant, that is that performance of device depend on architecture of device, and if it is yes, then how?
See, actually, while speaking itself, I told you, when we are talking about either slow wave device or fast wave devices, the cross-sectional dimension comes down with frequency. So when you are going for higher frequency, cross-sectional dimension is going to come down. However, whatever that rate of degradation is there with frequency for slow wave devices, it's much faster than the fast wave devices. And in fast wave devices, another beauty is there, we can work for higher order mode. So that for the same cross-sectional size, you can go for higher frequency. However, definitely once you are working for higher frequency and bigger size, there definitely beam wave interaction efficiency slightly comes down. So definitely architecture is going to play a role. Generally, instead of telling as the full architecture, generally we see the cross-sectional dimension of interaction structure. Yeah, next question.
Now, our final question is that how the term quantum state, black hole state, ghost state, and God particle state are related with each other.
Can you repeat your question?
Yes, sir. He has asked how the term quantum state, black hole state, ghost state, and God particle state are related with each other.
See, actually, what happened? Whatever these stages are there. See, when we are talking about the quanta, what happened? That is a kind of energy, correct? It is a photon energy. Fine, it is not a particle. However, hole is a missing of some particle, correct? So once the quanta was there, and when we talk about a black hole, it is a kind of a big sink. Like I will tell you one very interesting thing of electromagnetics. If you see the Gauss's law of electrostatic, there we call it that divergence of electric field intensity is rho by epsilon naught, correct? It is a charge density divided by free space permittivity, correct? Just suppose if you are able to make this permittivity, whatever this charge density is there, that is in numerator, in denominator you are having permittivity of free space, correct? It is a divergence. I am able to convey my point. I think little I am going in mathematics, but just you see left side I am having in the equation itself, left side we are having divergence of electric field intensity, and right side we are going rho by epsilon naught. For any reason, if this denominator, if I am able to make it 0, so what will happen? Divergence of a quantity will become infinite. Correct? So now you see, when divergence of a quantity becomes infinite, it means it is an infinite source. Correct? So that's similar. Actually, what happened? Definitely, because it is hypothetically it is possible. I can tell any permittivity, I can make it 0. Similarly, if I can make a permittivity minus, so what happened? It will become a divergence with minus infinite. It means it will become a sink. So the black hole concept is that kind only. It becomes a sink. What all energy goes around that, it closes that. So all these are at different stages, and it's very difficult. Actually, it cannot be correlated. One is particle, one is quantum energy, one is black hole. Is that way. Hope I could have answered the question whatever audience has asked.
Yes, sir, surely. And we have got appreciation in for today's session in the chat box as well as in feedback form as well.
Okay.
Yes, sir. So we will be concluding today's session with this, and I will be proposing vote of thanks now.
Okay.
So I deem it a great honor to propose the vote of thanks to all those who have helped us in making this session of today such a memorable experience. I, Dr. Asta Sharma, on behalf of EC Department, Jil Bajaj, extend a very hearty vote of thanks to our chief guest of the day, Dr. Vishal Kesari, for gracing today's FDP session. Thank you, sir, for taking out valuable time from your busy schedule and delivering such an insightful and thought-provoking session. We are very grateful to learn from you about so many things, and I am sure that definitely our participants would have also gained knowledge with such an intense knowledge which you have shared today. I would like to express a profound gratitude to our director, sir, Dr. Rajiv Agarwal, sir, as well as HOD, sir, for the continuous moral support and guidance. Also, I would like to specially thank Dr. Jaishankar Kesari for letting us to connect with you, with a speaker for today, and arranging this talk and helping us. We would have missed this opportunity if Dr. Jaishankar Kesari wouldn't have been there in our department. And also, I would like to thank all the professors for encouraging the students to the faculties and all to participate and guiding the participants too. We are very grateful to have the Department of Electronics and Communication as a great team. Each and every faculty is very sincere and they are actively engaged with this program throughout these 5 days. Finally, the wonderful participants for your unwavering attention throughout the session. Thank you so much for your cooperation. We will be meeting tomorrow. That is the final day of the FDP. So please make sure that you attend both the sessions because the tomorrow attendance links which we'll be sharing will be very important. And also tomorrow we will be having the talk of Dr. Satyakesh Dubey on the topic Antenna Design MIMO Systems. Thank you, sir. Thank you for providing such a good session and your valuable time. It's been such an intensive talk, and we didn't felt at all disconnected from your talk throughout the session. So that was indeed a great.
This pleasure is mine. Please convey my regards to all this faculty and your director. Yeah, thank you very much.
Thank you, sir.
Thank you, sir. Thanks a lot, sir.
Bye-bye for now.
Thank you, sir.